Okay, this is the 13.4 notes for statistics honors, and this will be the last lesson of the semester. Note that we do not cover 13.3, so if you're looking for it, don't worry about that. We are sticking with our chi-square test, but this time we're going to be just doing one called the independence test. So before we start that, though, just remember back in several sections back when we were talking about probability, we talked about a contingency table and how we can combine bivariate qualitative data into this type of table. So in this example, we have marital status and alcoholic drinks per month as our two variables, but basically the idea is that we would use, if you recall, marginal, joint, and conditional probabilities to find relationships between these variables. Probabilities of one's like widowed, given they abstain from drinking, those types of probabilities. So remember, this was the table total, and these were the marginals and all that good stuff. So anyway, so what if we want to do something totally different? So what if we wanted to see if there was a true relationship between the two variables that are being compared in the contingency table? Well, that is essentially what a chi-squared independence test does. So just from getting started here is getting your mind frame into, okay, we have a contingency table. We always have two variables in said contingency table, often called a two-way table. So what if I need to find if there is an association between those two variables? So let's start with the test. Okay, so it's the assumptions. If you look at the assumptions are exactly the same as the goodness of fit test. So that's good. So what did I mention in the other lesson? In reality, it'd be ideal if all of your expected frequencies or counts are larger than five or larger. But in reality, the letter of the law is that they should be bigger than one or bigger, so not zero, and that there should be very few that are less than five. That rarely happens, but when it does, be on the lookout for that. And of course, a simple random sample. The known alternative has changed. Why? In the goodness of fit test, we're looking for one distribution to be the same as another, whereas in this one, we're just looking for an association. Okay, so here's the deal. This is going to look a little weird. So the null hypothesis is that the two variables are not associated, whereas the alternative is that they are. So students will get a little confused about this because normally the null states some type of positive, they're the same, they're equal, blah, 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 whereas the alternative will be the opposite, that they're not. So this looks to be the opposite, but in reality they aren't, and I'll explain why. So I'll come back to that in 1 second. So step 3, you'll notice, is the exact same chi-square test statistic that we had in the goodness of fit test, the sum of O minus E squared over E. So again, we're dealing with the O and E variables for observed and expected. So realize what in the goodness of fit test, when the observed and the expected were the same, or generally the same, we would go with the null and say that, these distributions are similar. Well, if you think about it in this standpoint, returning to the null and alternative weirdness going on here, let's say if you have O and E are the same value, that means what you expected is exactly what was observed, which means that the variables that are the bivariate two variables are not interacting with each other to change anything. So if they're not, then that means they're not associated. So think about that for a second. When O and E were the same, you went with the null. Well, we have to do that again. So if O and E are the same, that means they're not associated in this scenario, which means the null has to be not associated. So yes, that's weird, but you just have to get used to it with one another. Another way to look at it, too, is that if the null hypothesis was that the two variables are independent of one another, which would be logical, that means that they are not associated. So there's a bunch of things going on here to give you clues on not being associated, but basically that's the setup for the test. Okay, so let's return to our example I'm going to read here. It says, suppose a national survey was conducted to obtain info on the alcohol consumption patterns of U.S. adults by marital status. A random sample of 1,772 residents, 18 or older, yielded the data displayed in the table below. So basically we have single, married, widowed, divorce as the categories for marital status. We have, for alcohol drinks per month, we have abstaining 1 through 60, and then the dreaded over 60. So basically, what did they do? They sampled 1,772 residents, 18 or older, and they got the totals over on the right and on the bottom, all the data, and then, of course, the table total. So it says, suppose that our main focus to determine if alcohol, that's fantastic, I'm ahead of myself here, marital status and alcohol consumption has some type of association at 1% significance. So when we look at this, the null and alternative will look like what? Remember that the null is that the variables are not associated. So we would say marital status and alcohol consumption are not associated. So the alternative will be that they are. And that's all you have to write for the null and alternative hypothesis. Okay, so how do we get started with our test? Well, as we said before, so these are essentially the observed counts. So we need some expected counts to compare them to. So how do we find those? Well, in our problem, we weren't given any type of claim distribution, which you would actually never be given in this type of problem. So the expected counts have to come from somewhere, and we can't really use this goodness of fit formula to do it, because even though we have n, we don't have any percentages at all. And not to mention the fact the formula really only works for one variable worth of data. Whereas with this, we actually have two variables worth of data that we're dealing with. So basically the summary of the story is there's a new formula. What is that formula? Equals R times C over N. So we know what N is. That's the total amount of folks in the study, right? So that's going to be super easy, like for example, table total. But what does R and C mean? Well, R is the row total for that category, and C is the column total for that category. So all we're going to do is multiply those two and divide by n in order to find expected count. So let's try a example of that. So it says right here, we already know that the observed frequency O for the top left cell consisting of single and abstain is 67. Okay, so remember that was here. So that was our O for our variable. So let's use this new formula to find the expected frequency for that same cell. Okay, so this is how you do it. It's super simple, nothing complicated. I'm going to leave this marked. So the key is that we are dealing with this row and this column in order to generate the 67. So what is the row total of this column? It is 354. So that is R. What is the column total of abstain? It is 590. And then what is the table total? It is 1772. So this formula will create our expected count for that cell of the contingency table. So you'll notice, what did I do with that value? I placed it underneath the observed value. This is a pretty sort of universal method for determining expected counts, though I often see them with, let's say, like brackets around them or something, just so that they are sort of separated from the observed count. So what does this mean? This means that even though we observed in our study 67 who were single and abstaining from drinking, the expected number should be 117.9. Okay, so our goal here is to basically fill out the rest of this table with all the expected counts. I'm sure there are some interesting ways to do this, but there's just a lot of work that you have to go through here when you're doing this from scratch. This can be very simply done on the calculator, by the way, which we'll talk about a little bit later. But for now, what are you going to do? So I'm going to sort of go through and do a couple more with you, just for argument's sake, so everybody understands the process. So let's say we move to, let's just pick a completely different one. So let's say we go to 51. So how would we find this expected count? We would take the row total of widowed on 51, which is 143. We would multiply by the column total, which is 957, and again we would divide by 1772. Turns out that that value is about 77.2, which we would put underneath the value, 77.2. Okay, so let me get rid of the brackets here. They're not that important. I got rid of a lot more. I'll put that back. Okay, so you would want to do the same calculation for all of them. I will show you how to do this in the calculator soon in terms of like a shortcut, but for now, it would be ideal just to do a couple calculations and make sure you understand the process. If you do so, you can pause and do it on your own, obviously, but I'm going to go through and put them all in here. Okay, if you do all those calculations for all the expected counts, you get the following values. Okay, so what is the hypothesis test about? Similarly to the GOF test, the goodness of fit test, I'm looking at all of the observed counts, which are the top numbers, versus the bottom numbers, and I'm saying, are they somewhat similar? So if you go to like married and 1 to 60 drinks, it's almost identical, right? Like that's as close as you're going to get. If you go to some of the other ones, they're pretty close, you know, and then you'll go to some others and you go, whoa, that's really far away. That's pretty far away. So basically, the idea is how well the O's match the E's will depend on whether you reject or do not reject the null hypothesis. So what we have to do basically is we have to treat all of this as, oh my goodness, we have to treat all of this as basically taking, for example, single and abstain would be one variable. Single and 1 to 60 would be another variable. Single and over 60 would be another. Married and abstain would be another. So essentially, every single one of these cells in the table represents one calculation that you have to do. What do I mean by calculation? Well, again, we have to calculate the chi-squared test statistic using the same formula. So we have to do that for every single outcome, and every cell is an outcome. So if you count this, this is a 3 by 4 version. So there are 12 outcomes that we have to calculate this formula for in the scope of what we're doing. So there's one small thing though, before we get to that. The degrees of freedom also has to be different. So the degrees of freedom in our scenario is r minus 1 times c minus 1. So what is that? That is the number of row variables minus 1 times the number of column variables minus 1. So if we're going to actually calculate that, it would be pretty quick, right? So it would be 4 minus 1 times 3 minus 1, which is 3 times 2 is 6. So that would be our degrees of freedom. We'll do that in a second. But basically, that is the idea when it comes to calculating degrees of freedom for a chi-squared test statistic. Okay, so returning to what I was talking about. So in this scenario, if we have to calculate this formula here, you'll notice this chart should be very familiar to you. This is what you did in the previous section. But again, every one of these cells, all 12 of them, represents one row of the calculation table. So there are 12 calculations that we have to do. So what could you do? Again, you could do L1, L2, and go ahead and do your L3, L4, L5, and find all of these values if you like. You're not really going to do that much after this, but it's obviously valuable to see how those come together. So you could plug these into your list right now and come up with that if you like, and feel free to do that. But I'm going to pause this and fill in all the values so that you have them. Okay, starting up again. So here are the values that you would calculate if you go ahead and did the lists, or even if you did them separately. It's up to you. But basically what will happen is you'll subtract the first two columns to get this, you'll square that column to get this, and divide by your E column to get this, and you'll end up with a sum of 94.4, which will be your chi-square test statistic. So again, your critical value and p-value approaches all the same. They do list the new degrees of freedom, which is the change. Why don't we write that out? So I'm just going to be, very clear with this. So it says, since there are 4 categories of marital status and 3 categories of alcohol consumption, our degrees of freedom would be 4 minus 1 times 3 minus 1, which is going to be equal to 3 times 2, which is 6. So there's our degrees of freedom. So let's say we want to follow the critical value approach, then we would be looking up in the same table chi-squared 0.01 at degrees of freedom 6. So we can go to chi-square here. That's not an eraser. What is happening? Okay, we're a little stuck here. There we go. So we would go to 0.01 at degrees of freedom 6, and we would get 16.812 as our critical value. Okay, next page, let's do our usual routine. So what do? We mark our critical value of chi-squared 0.01 df equals 6 would be equal to 16.812. This creates our rejection line in our right tail because we in chi-squared, again, it's a right skewed distribution. We would then take our a very large chi-square worth noting here, 94.4, which is way out here somewhere, and we would say clearly what would be our decision. So we can clearly say that our chi-square test statistic, 94.4, is to the what of our critical value, 16.812. It's to the right. Therefore, we reject H naught by a mile, by the way, right? Then how would we interpret our results? So what does this mean in this standpoint of what we're doing? So we would go down and we go to our known alternative, which was way back here, right? Known alternative. And what does that mean? If we reject H naught, we're basically saying that marital status and alcohol consumption are associated. That is going to be our, summary. So if you want to just make a note of that, the variables will be associated. Okay, and of course you can do you might be asked. You usually aren't in this setting with this remote setting, but basically you would do we reject H naught. It provides evidence at the alpha blah 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 that the variables will be associated. So, but that's the conclusion we're coming to when it comes to our problem itself. And of course the p-value method is fine. If you want to do that, chi-squared CDF, we would take our test statistic, not our critical value, but our test statistic. We would go to one very large number at 6 degrees of freedom, and then we would get some p-value, which I don't have in front of me, but it's going to be massively zero from if I was to guess, because this thing's a mile out to sea. So we would reject H naught by a mile. Just a small thing here. I put this on here just because if you remember the the causation concept with correlation, just as the same thing here. Just because we conclude that the variables are associated doesn't mean that one causes the other. So we would need to do a well-defined experiment, which we don't really cover in this course, but we would have to do a well-designed experiment with placebo effect and control to determine if there is any type of causation involved here. We basically just say they're associated in some way. Whether that's from another lurking variable or not, we don't know, but that's all this test is saying. That's my summary here, is that don't go off the deep end here and assume that it's something else. Okay, so now that we've gone through this test, I'm just going to sort of be honest with you here. The reality is that when you're doing a goodness or an independence chi-square test, this is craziness. Can you imagine having to do this on, let's say, a live exam where you're in class? It's not fun. And yes, you'll be home doing this in this remote setting, but just generally, like, it is not a fun. Think about if we actually increased like another category or something like that, and all of a sudden let's say we had another category for drinks per month. We would be going to like a 4x4 now, 16 instead of 12 we have to do. It is just insane. So it turns out that in the calculator, you can use the matrices in order to pull this calculation off in a very quick manner. So what I usually do in this very last section is I tell students to just use the calculator. So I don't have them run through these crazy calculations here at all. I like that you do it once, you saw it, you know what you need to do, you see that it's similar to the goodness of fit test, which is much easier to do in terms of calculations. There's usually only 3, 4, or 5. But for this is getting a little crazy. So in the calculator, we have what's called I'm going to move to here. We have what's called we had the GOF test, but we're just going to chi-squared test. So for the chi-squared test, when you bring it up into your calculator, which I want you to do now, I think it's C, by the way, you actually get the following. It says observed, expected, and then the rest is not important. So in observed, you'll see this, and in expected, you'll see this. So these are actually, when you have these brackets like this, these are called matrices. So what is this test asking you to do? It's asking you to put your observed counts in matrix A. If you put your observed counts in matrix A, then you can just run this test and you'll be able to find your calculations. That's all you have to do. You put the observed counts in matrix A, which I'll show you in a second. This means that when it's doing the calculations, the calculator will store expected counts in matrix B. Okay, so I'm going to put observed counts in matrix A. Whereas the calculator, so this right here, you don't have to do anything with matrix B. The calculator, all you're doing is telling the calculator where to put the expected counts. So that's weird, and I know you don't know what this means yet, but that is it. That's all you have to do to run this test, is you just have to take all the let me put in green here. You have to take all the observed counts and put them in a matrix. So let's just talk about matrices for a second. I know a lot of students are not comfortable with matrices, but the idea is a matrix is a way to put data together in like a table. So like what you would do in a matrix is you would say, okay, so there's 4 rows and there's 3 columns. So this is a 4x3 matrix. So you would have 67, 213, 74, 411, 633, 129. You would have 85, 51, 7, 27, 60, and 15. So this is the matrix that you will need to enter into the calculator. So you might say, well, how do you do that? Well, if you quit out and you go to, believe it or not, there's above x to the -1. If you hit second x to the -1, you're going to see the term matrix. If you go over to edit, then what you're going to see on the page, if this is the first time you do it, is you're going to see the following. You're going to see matrix A 1 by 1, and then you're going to see like something that looks like this. Okay, so what is this here? This is the dimensions of your matrix. So you're going to move your cursor so that it's highlighted on the first number, and you're going to change it to a 4, because what kind of matrix do we have? We have a 4 by 3, and you're going to change this number to a 3. So what's going to happen? When you change those numbers to a 4 and a 3 and press enter, hold on, all of a sudden your matrix is going to turn into a 4 by 3 matrix. You're going to go into that matrix and enter these numbers. So 67 to 13, you're going to go through the whole process. As you go through, enter the numbers, and when you're done with entering the numbers, if you want to pause it here to do it, then I'll come back in a second and show you what you're doing, what's supposed to do. Okay, so now you should have all of that in matrix A. So this is officially stored there, essentially, right? Where you're supposed to go. So once you have it in there, you can quit out, you can return to your test, which is chi-squared test, and since now you have your observed, you just press calculate. If you press calculate, what's going to happen for your chi-squared test? You're going to get a chi-squared of 94.26. You're going to get a p-value, which is 3.9 times 10 to the negative 18, wholly approximately 0, and df is equal to 6. So literally, if you look back at our calculations for this, what did we get for chi-squared? We got, we got 94.4, which is awful darn close to 94.26. And we said our p-value would be 0 when we did it, approximately 0, and indeed that's exactly what we get. So this was actually pretty good. Now, one thing to note though, a lot of times you're going to have to show the expected counts. Why? Because what are our assumptions for our test? Our assumptions are all about checking the expected counts to make sure generally that they're 5 or greater. So that means we need to display the expected counts somehow. But where did we store them? We stored them in B. So if we go back to the matrix command, and all we have to do on names, you can do edit or names, it doesn't matter, but if you want to, well, just go to edit because that's what you're used to. If you press enter on it, it'll show you all the expected counts in matrix B. So if you go into our big table here, you should check 117.9, 191.2, 44.9. You'll see that they are all the same or similar to the counts that were calculated manually before. So yes, there's a lot going on. If for some reason you're just blown away right now by the calculator, that's perfectly fine. It's a lot, and it's in class, so it would be so much easier for me to show you, but I can't, and I can't stop with you here. So my suggestion is, if you're lost when it comes to the calculator for this, use the calculator command guide in Canvas. It is excellent. If you haven't done already, literally not only does it show a list of every little step that you do with pictures and the calculator there, but it also has an accompanying video that you can show or you can follow in order to accomplish this. You'll be experts within 15 minutes of going through it. So just my suggestion for the examples we're going to do is we're just going to do it on the calculator. That's it. There's no reason to do all of these crazy calculations. You get where they come from. Yes, in case on an exam situation they go, what's the expected counts of married and over 60 or something like that? You need to be able to calculate this and understand that, but there's no reason in doing 12 or 16 or even more of these when you can just use the calculator to figure this out. So my suggestion is to do exactly that. Become an expert with the calculator on the chi-squared test. And that's exactly what we're going to do for these examples. Okay, number 1, the contingency table shows the results of a random sample of 2,200 adults classified by the favorite way to eat ice cream and their gender. At alpha 0.01, can you conclude the variables favorite way to eat ice cream and gender are associated? Okay, so again, we're going to use chi-squared test to do this. Okay, very simple, straightforward. We're not going to do all the calculations. There's no need to do that, so let's just go ahead and go through the test. So what is the null going to state? That the two variables are not associated. So we would write that out. We would say ice cream preference and gender are not associated. Okay, note that this is exactly the same as saying ice cream and gender are independent, which, they're analogous. So what about alternative? That would basically be ice cream. You know what I'll have you do? Just say, just like I did last time, just say they are associated. Okay, let's shorten that so you don't have to write out a lot, but you know the gist. All right, so once we have this, we can go right into entering the data. So what are you doing? You're going to go into the matrix menu, right? You're going to go into the matrix menu, which is above x to the negative 1, and you have a 2 by 5 matrix. So you change the matrix dimensions in edit to 2 by 5, and then you enter the numbers in the table. Okay, so when you do so, you'll have them all entered. If you want to pause right now to put them in there, you'll get what you see here. Once you get that, then all you have to do is go to the chi-squared test and have A and B again. It'll just overwrite what's there as you're observed and expected, and basically, put in the numbers that you have. So what do you end up getting when you do that? From the calculator, you will see that we have so I'm going to write from chi-square test on TI-83 or 4. Okay, we're going to get a chi-square test statistic of 23.49. We're going to get a p-value. It says 1.10 to the negative 4, which is the same as this. Right? These are all approximate. And of course, worth noting, the degrees of freedom is equal to 4. I want to point that out, though, just in case that comes up somewhere on a test. So if this is 2 by 5, that means our degrees of freedom is equal to 2 minus 1 times 5 minus 1, which is 1 times 4, which is 4. I just want to point that out, right? So you understand where that came from. So we get this as our result. So all we have to do basically is look at our p-value and see that it's less than 0.01, so we would reject H naught and claim that the variable gender and favorite or ice cream preference are associated. Okay. One small thing that we have to check, again, we need to make sure that the expected counts for the assumptions are ideally bigger than 5. Even though we have. So we want to go to, if you want to go to edit and press matrix B, it looks like the smallest expected counts, we'll put them in here actually. So we got 546.55, we got 346.36, 209.45, 24, 73.636, 61.364, we got 20, 174.55, 288.64 and 455.45. So hopefully you found that in the matrix command to find them, and those are expected counts. Lowest one is 20, so we're clear, all bigger than 5, so the assumptions check out, and we have a random sample. So this is unique because normally we check assumptions before we do a problem, but we can't actually do it until we run the test, because that's what's spitting out the expected counts. So I usually do it last just to make sure that my result was valid. So that would be the best thing to do. Okay, last one. Contingency table shows that symptoms of a random sample of 565 subjects in a drug trial. Each subject was given either the drug itself or the placebo, then asked if they were feeling nauseous. At alpha 0.05, can you conclude that nausea was associated with the drug? Okay, so alternative and null. So null is that nausea is not associated with the drug. other words, nausea and the drug are independent of each other, whereas the alternative is that they are associated, which is fine to write. Okay, so what would you do? You would go into your calculator, you would enter a 2 by 2 matrix, plug in these 4 numbers, and what will be spit out? Well, let's just first, before we do that, what's the degrees of freedom? We can do that calculation. 2 minus 1 times 2 minus 1 is 1 times 1, which is 1. So that's a weird degrees of freedom, but that'll show up when you do the calculation. So chi-square in the calculator is 10.53. And your p-value is approximately 0.001. Okay, so that is less than 0.05, so we would immediately just say that we reject H naught, and we would say that the drug is associated with nausea for the purpose of our experiment. So that's pretty straightforward in terms of what we're doing, very easy. An interesting side product of this, by the way, before we get to the assumptions, is that note that this was an experiment. So they used the placebo, right? We could learn more about this, but this was clearly an experiment. So this is the type of scenario where we might be able to determine causation and more than an association, but this is the test that you would run to determine that. So interesting byproduct of this, because experimental, we might be able to go beyond association and actually say that the drug does cause nausea as a side effect. But what about assumptions? There's not a lot of space in the table, so I'm just going to make an expected table. So if you go into your matrices and so this is nausea, no nausea, this is drug, placebo. So if you go in and you copy down the expected counts in matrix B, they're going to be the following. If this was a live exam situation, I would always have you provide me the expected counts as proof for checking your assumptions, by the way. But since this isn't, I don't know how the test is run. I didn't make it yet, but you want to be able to do this anyway. So your expected counts are all bigger than 5, so you don't have to check bigger than 1. It looks like we have a random sample, so all assumptions are met, and this is a valid result based on our test. So that is it. So just as a summary, I would advise for 1 and 2 that yes, you know where the expected counts come from in terms of the formula and where degrees of freedom comes from in terms of the formula, but when you're running the test itself, I would use the matrices and chi-square test. It's so much faster and you can get through it pretty quickly, and that's a wrap.